guys, and welcome to the stage number 4 of this selected topics of physics. In this video, you will learn about oscillations in waves, sound, and optics.
So, an oscillation is a kind of motion that is repeated in a period of time. Acoustics is that science that studies the sound, and the optics studies the light. Now, you may be wondering, how is a spring related to the alarm that wakes me up every day and the light I can see through the window? So let's figure it out.
Before we start with the content of the stage, I'd like to thank the teacher Alejandra Salinas for giving me these slides so I could share them with you. Waves and oscillations. First, we need to define the periodic motion. Movements that repeat themselves with the same conditions of place, speed, energy, etc. after a given period of time. The period is the minimal time in which the conditions of motion are repeated. And the frequency is the number of times that the process repeats its conditions for each unit of time. The simple harmonic motion is a variety of periodic motion that is tensile because it presents motions in which the mass repeats its trajectory. An example could be maybe a spring or maybe a rotation of something. It has two main features. The first is the magnitude of motion or amplitude, and then we have the restoring force. This is a force that takes the object back to its equilibrium position. Another example of simple harmonic motion could be the pendulum. The pendulum is any body that can oscillate from a point of suspension. The oscillations are related to the wave motion. But first we need to define a wave. A wave can be defined as the propagation of energy in space without transfer of matter. Also, there are two main classifications for waves. Waves are classified according to the medium in which they spread. If we talk about this, we can mention the mechanical waves and the electromagnetic waves. A mechanical wave is a wave that needs a medium to spread out. An electromagnetic wave, they don't need any medium to spread. According to the type of motion, we may talk about transverse waves and longitudinal waves. A transverse wave is a wave that oscillates perpendicular to the spread, and a longitudinal wave is an oscillation parallel to the spread. So, taking the transverse wave as an example, we may find the crests, which are the top parts of the wave, and then we have the troughs. The troughs correspond to the bottom part of the wave. And finally we have the nodes. The nodes are those points where the wave is found in the equilibrium line. This wave also has some features. First, the frequency, which is the number of waves that pass through a determined point per unit of time. Then we have the period. The period is the time necessary for a disturbance to spread a distance equal to one wavelength. And the wavelength, in general, indicated by the Greek letter lambda, is defined as the minimum distance between two points that have an identical state of motion, that is, the separation between two consecutive crests. And then we have the amplitude of the wave, which is the maximum displacement needed to reach the point of medium measured from a position of equilibrium. And finally we have the speed of wave, which is defined as the speed of propagation of the disturbance. Waves may present different phenomena. The first one is the reflection, and this is the most common one. When a wave comes up on a boundary that separates two media of different properties, part of its energy returns to the first medium and the remainder enters to the second medium. When we refer to the energy that returns to the first medium in which the wave began, we are talking about the reflection. A wave can also experiment the refraction. This phenomena is presented when a wave passes through a medium with different properties. As the media have different properties, the speed of propagation of the wave will be different in each one. The wavelength will differ, but the frequency remains constant. Due to the change of speed, a deviation occurs in the direction of propagation of the ray. And then we have the superposition. which is determined by the superposition principle. When two or more waves propagate through the same medium, the resultant displacement at any point is the algebraic sum of the displacements produced by each wave separately. Interference is a special case of superposition, when the waves that are superimposed have the same frequency and same wavelength. If the crests and troughs of the superimposed wave match, the resultant wave has a greater amplitude. We can say that these waves are in phase, and we call it constructive interference. But if the waves are in opposite phases, this is called destructive interference. Diffraction is the phenomenon which takes place when a wave encounters an obstacle and it cannot pass through. So, it passes around it, creating a disturbance behind the obstacle. The stationary waves correspond to another case of superposition of waves. An stationary wave is produced when two waves of equal frequency and amplitude propagate in opposite directions and then they overlap. All bodies have a natural frequency of vibration. When a source emits waves and they match with the natural frequency of vibration of an object, the body begins to vibrate with an increasing amplitude. This phenomenon is called resonance. Now it's time to talk about acoustics. Acoustics is the science that studies the sound. And the sound is defined as a mechanical wave that is propagated through an elastic medium, which is the form where the wave passes and recovers its shape after the wave has passed through it. The human being can hear between 16 Hz and 20,000 Hz. This is called as the audible range of human ear. Waves above 20,000 Hz are known as ultrasonic waves. Waves that are less than 16 Hz is what we call infrasonic waves. The sound can travel through the air at 330 meters per second at temperature of 0 Celsius degrees. By increasing the temperature of the air, it also increases the speed of the sound in almost 0.6 meters per second for each degree. So, the speed of the sound can be measured with this expression. The human ear detects the characteristics of sound waves, the pitch, timbre, and loudness. The pitch is the frequency of the wave. That is, at a higher frequency, sound is higher or snitcher. At a lower frequency, it is lower or bass sound. The timbre is the quality of the sound waves, and it's characteristic of each instrument or each person. Loudness or intensity describes the amplitude of a wave and is measured in decibels, and determines whether the sound is strong or weak. The intensity of the wave is the ratio of the power per unit area. The range of intensity audible to the human ear is between 1 watt per meter square and 1 times 10 to the negative 12 watts per meter square. The extremes are referred to as a threshold pain and audible threshold. It's pretty common that in acoustics, the audible threshold is called 0 in sound intensity. The intensity level is the measure of the intensity of sound in relation to the zero standard of intensity. That is, it is the volume of sound on an arbitrary scale in relation to the sensation of loudness, and its unit is the bell. Another interesting effect in acoustics is the Doppler effect. The Doppler effect is present when there is a relative motion between a source of sound and the receiver or observer. When this occurs, the frequency perceived by the receiver is affected by the said motion. Increasing if the transmitter and the receiver are closer to each other, and decreasing when they are farther away. It's very important to understand that the Doppler effect analyzes the change in frequency of the waves, and not their intensity. So here we have two different equations we may use depending on the case we have. So F apostrophe is the apparent frequency. Vs equals the speed of sound. Vo equals the speed of the observer. And Bf equals the speed of the source. F obviously corresponds to the frequency of the sound. Let's see an example so we can understand Doppler effect better. It says, a factory whistle sounds with a frequency of 800 Hz, a day in which the speed of sound equals 240 meters per second. For letter A, we have the case. What apparent frequency of sound would a person who is approaching to the factory at a speed of 30 meters per second receive? So we need to use this equation and then substitute the data. Finally, when we obtain the result, we get that the apparent frequency equals 870.58 Hz. Obviously, the frequency is higher than the original one, because they are getting closer. And then, for letter B, we have another case. It says, what is the pitch of the sound heard by a person moving away from the factory with a speed of 30 meters per second? In this case, they are getting away. So we need to change the signs of the equation. And by solving, we obtain that the apparent frequency equals 729.41 Hz. In this case, the apparent frequency is less than the original one, and this is because the source and the observer are getting away. Finally, it's time to talk about optics. Optics is the branch of physics that studies light and the phenomena it produces. Optics has two different approaches. The first one is called geometric optics. This studies the behavior of light propagated in straight lines called rays. And then we have the physical optics, where we consider the light as a wave. This is including all wave phenomena we have already talked about. And finally, in some more modern studies we have the quantum optics. This one considers the light as a corpuscle, that is, consisting of small particles that move and impact on objects, making them visible. Albert A. Michelson used the Foucault's method in 1850, and he obtained a very accurate measurement to determine that the speed of light in air is 2.997 times 10 to the 8 meters per second. Today, the value accepted for the speed of light is this one. But to make it more practical, we only said that the speed of light equals 3 times 10 to the 8 meters per second. The electromagnetic spectrum is made up of different kinds of electromagnetic radiation present in an electric field and a magnetic field. The spectrum of visible light is located between the wavelengths of 400 nanometers for violet light and 700 nanometers for red light. The dispersion of light is the phenomenon which creates the colors of the rainbow. Newton demonstrated that the light is formed of a various color, making up the primary color of light red, green, and blue, and the secondary colors of light yellow, turquoise, and magenta. The reflection has already been defined as the phenomenon that describes how light returns to its original medium as a result of impact on a surface. When the surface is smooth and reflects the rate of light received, it's called mirror. The ray of light that touches a surface with an angle of incidence is reflected with one angle of reflection. This is known as the law of reflection. When an incident ray of light touches an irregular surface, the ray of light reflected is not well defined, and the light is scattered in all directions. This phenomenon of light is called diffuse reflection or diffusion of light. On a plane mirror, the reflective surface is flat. A mirror of this type forms a virtual image, which is seen inside the mirror and is symmetrical to the actual image and at the same distance of the mirror. A spherical mirror is formed by a section of reflective sphere. We have two types of spherical mirrors: the concave mirror, in which the surface of the inside part of the sphere is reflective. Then we have the convex mirror, in which the reflective surface of the outside part of the mirror is spherical. The focus or focal point in which the rays reflected coincide is the midpoint of the radius of curvature. A concave mirror is called converging mirror. Remember, we had said that refraction of light occurs when the light passes from one medium to another with some different characteristics. The rays that touch the surface are called incidents. The rays that are reflected as they pass the surface are called refracted. The ratio between the sine of the angle of incidence and the sine of the angle of refraction has a characteristic value called index of refraction. So, when light passes from one medium to another with a Lenser density, if the angle of incidence is large enough, the refraction can reach the 90 degrees and the refracted ray will disappear. This phenomenon is known as total internal refraction. The angle of incidence in which the total internal reflection is characteristic of each medium is known as the critical angle. Lenses are transparent objects made of crystal or transparent plastic and are limited by two surfaces, one spherical and one flat, or by two spherical surfaces. These are two types of lenses. The convergent lens. The convergent lens converges and refracts a parallel light at a focal point beyond the lens. The divergent lenses. This one refracts and diverges parallel light from a focal point located in front of the lens. I want to thank your attention, and once again, I'd like to thank teacher Alejandro Salinas for providing us this incredible material. Thank you.
Well, so this is how we finish the stage. And this is also the end of the course. I hope you learned a lot. And now you may be able to find explanation to those physics phenomena you can see every day. Goodbye.